This lesson is Mrs. Gucci's College Now Pre-Calculus class. This is video 4.2, and we are working on exponential functions and their graphs. So if you would just open up file 4.2, and we should be on page 1.12. Okay, so when we get into applications, we mainly start to be concerned with word problems. And when we're dealing with exponential functions, one of the big types of word problems we deal with is interest rates, compounded interests, and problems of that type, investment type problems. So we're going to take a look at one of those. So the amount of money A to which a principal P will grow after T years at interest rate R in decimal form, compounded n times per year, is given by the function A of T equals P times 1 plus R divided by n raised to the n times T. So this formula here, you've actually seen this formula before, and we're going to be using this formula extensively. So you do have to know this formula. I'm not giving it to you. You have to have it memorized. Okay? So suppose we have $100,000 and we invest it at an interest rate of 6.5%, and it's compounded semi-annually. Semi-annually means that we compound the interest twice per year. Okay, and that should have an E in there. I apologize. Okay, so twice per year for semi-annually. We want to find a function for the amount to which the investment grows after T years. So we're going to kind of start by taking that formula and putting in the information we know. So, again, we have our formula, and this is for part A. We've got A of T equals P, meaning the principal, 1 plus the rate divided by the number of times compounded per year, raised to the number of times compounded times how many years. Okay. We want to find a function for the amount to which the investment grows after T years. So we're going to be keeping this T. We want to know how many per T years. So we know what our principal is. Our principal is $100,000. That's what we start with. 1 plus the rate, which was 6.5%. Now, if you remember, we can't put percent in, so you do have to change that to a decimal. Okay, moving the decimal place 2 places. So that's going to be 0.065 over the number of times per year. So since it's semi-annually, it's twice per year. And then again, twice times the number of years, and we're doing it in terms of the number of years. So we're going to leave that T right in there. So that is your function in terms of the number of years. Okay. B is asking us to graph it. So we're actually going to go right to our graphing calculator for this one. We're going to work with our windows to see what's going to be appropriate for the problem itself. So go ahead and insert a graph page. And we know our function. Okay. We just determined that. 100,000 times 1 plus 0.065 divided by 2 raised to 2, and we're going to use x. Okay. So there's our function. Now, if we think about it, it's not going to... I see my mistake already. This needs to be changed. There we go. That's better. And it's not going to show up when we graph it because we have to deal with our window. Since our x-axis, this is going to be our time in years. It doesn't make sense to deal with negative years. So we want this to be starting at year 0, and then we could say 30 years would be an appropriate time. Usually that's how long a mortgage is. Now, when we talk about our y-axis, this is the amount of money in the account at the end. So we're starting with 100,000. We're going to want something quite a bit larger, so maybe 500,000. So let's adjust this. All right, I'm going to use menu. Window settings. My X minimum, again, I don't want negative years, so we're going to change that to 0. My X maximum, I want it to be 30. My scale, I can leave it auto. My minimum Y, if I'm starting at 100,000, I really don't need any negative values there either, since this is appreciation, not depreciation. I'm going to start it at 0 just to give us a nice even look. And then if we start at 100,000, we know we're going to be having growth, so let's make it 500,000. And okay. So we get a nice exponential curve that's increasing. All right, so there's our graph. Okay, so C wants us to find the amount of money in the account at t equals 0, 4, 8, and 10 years. When will the amount of money in the account be 400,000? So since I have a function, this is actually very simple for us to calculate. Okay, we've got a nice function for us here. Put that in calculator. So C is just evaluating. So if I want it at t equals 0, 4, 8, and 10. We're simply evaluating into the function we created. So we're going to find a of 0 just by plugging 0 in for t. And all I did to get 1.0325 is I put this right in my calculator. And then that's 2 times 0. And since this becomes 0, anything to the 0 power is 1, which leaves a of 0, or the amount of money that I begin with, as 100,000. Okay. A of 4, same process. Two times 4. I'm just going to put that in my calculator. So at the 4th year, I'm going to have $129,157.75. And you do want to round it cent appropriate. A of 8. Now you could also pull this up on your table from your graph. That would work as well. And take a minute, put that in your calculator. You get 166,817 and 25 cents. And last, 10th year. Put that in your calculator. $189,583.79. All right, so to find the amount of time it takes for the account to grow to $400,000, what we need to do is we need to take our equation and set it equal to 400,000. We want to know when it equals that. So what we're doing is we're in search of the value of t that's going to give me 400,000. Okay. So we can do this by graphing. That's a pretty simple way to do it. So I already have my graph in here. So all I need to do is now pull up my function bar and put in 400,000. What I'm looking for is when these two lines intersect. That's when I know my function in brown is equal to 400,000. So a nice way to do this is menu, analyze, intersection, lower bound, upper bound, and here we have our value. Okay, and since we're dealing with years, after how many years, that's going to be my x value, that 21.7. Okay, so about 21 years and 8 months approximately. Okay. All right, so the next thing we're going to talk about is the number e. The number e is an irrational number, just like the number pi is, except this decimal approximation is about 2.71828182884, and it does keep going on. And we wind up using the number e quite a bit when we talk about compounding continuously, again with that kind of interest rate. Okay, so we're going to talk about this next. Okay, so we're going to find each value of e to the x to 4 decimal places using e to the x on our calculator. So this should be very simple for us to do. First one is e to the 3rd power. So I'm going to go ahead and insert a calculator page. And we have an e to the x button right here on our calculator. So that's what we're going to use. E to the 3rd power. So to the nearest 4 decimal places, we have 20.0855. Okay, so the next one we're going to do is e to the negative 0.23. And to the nearest 4 decimal places, we get 0.7945. Stop looking at me, it's creepy, guys. All right, and the last one is e to the 0. And anything to the 0 power is 1. All right, so the next thing we're going to look at is graphs of exponential functions with a base of e. So this is going to be quite a bit of graphing. So what we're going to do is we're going to take a look graphically at e to the x and e to the negative x to see what the differences between the two are. And we're going to do that right on a graph page. And again, we're going to use our e to the x key, and we need to place in our x. So there's e to the x. It's increasing from negative infinity to infinity. E to the negative x is decreasing on the interval negative infinity to infinity. Okay, so basically what has happened here is it's a reflection. The black line is a reflection of the red line over the y-axis. We make the x values negative. Okay, so we're going to graph the following by hand. Before doing so, we're going to describe how the graph can be obtained from the graph e to the x. So e to the x, again, is our parent function. What happens when I add 3 to the x values? So if we think about that logically, let's say I have the point 1, 2. What I'm doing is I'm adding 3 to my x. So this point would become 1 plus 3, which is 4, 2. So what's actually happening to my graph is I've gone from 1, 2, say it's to 4, 2. Okay, so it looks like I'm going to move to the right 3 units. So let's see if that's correct. All right. So again, e to x is our parent function. And then e to the x plus 3, that's an ln. We thought that it was going to move to the right 3 units, so we're going to see if we are indeed correct. Oh, and we move to the left. Okay, so remember, going back and remembering our rules, if we're adding or subtracting directly to the x, it moves it in the opposite direction than we think about, right? So we have to be careful with that. So if it's addition, we're moving left. If it was subtraction, we would move right. Okay, so that's one of those tricky ones. And I'm glad we got it wrong, because that's a nice learning curve there. Okay? All right, so graph the following by hand. Before doing so, describe how the graph can be obtained from the graph y equals e to the x. So we have e to the negative 0.5x. And now, when we looked at our original function, if you remember, e to the x looked like this. It increased, right? And as soon as we made it negative, it decreased. So I'm going to assume that it's going to decrease. And then this 0.5 is going to change either how quickly or slowly the decrease is. There's our e to the x. So what it did is it reflected it over the y-axis, and then it looks like it's decreasing at a slower rate than our original. Okay. Okay, graph the following by hand. Before so, describe how the graph can be obtained from the graph e to the x. So we have quite a bit going on here. I do have a negative x, which means I am going to have a reflection over that y-axis. And that negative 2, I assume it's going to make it decrease faster, because when it was a decimal, it decreased slower. And we also have to deal with this 1 minus. So we're going to have to see what happens there as well. I'm thinking it's going to be some kind of vertical shift. So let's take a peek and see what happens here. So again, e to the x is our parent function. And then we had 1 minus e to the negative 2x. Okay, so we did have a reflection over the y-axis from that negative. 1 minus did shift it down a unit. And it also, because it's a negative e to the x, reflected over the x. So again, reflection over the y, then a reflection over the x, and a translation up 1 unit. Okay, this is a plus 1, so up 1 unit. Okay, that's it, guys.